किसको? मॉनिटर को? अभी रखूँ मैं उठा के?
नहीं।
अच्छा, इस क्लास के बाद? अच्छा।
शिफ्ट करना पड़ेगा।
गुड आफ्टरनून एवरीवन। वॉइस तो आ रहा होगा ना? अच्छा। गुड आफ्टरनून, गुड आफ्टरनून, गुड आफ्टरनून, गुड आफ्टरनून एवरीवन। गुड आफ्टरनून, गुड आफ्टरनून, गुड आफ्टरनून। काफी ठीक है, ठीक है। ठीक है, करते हैं स्टार्ट है ना? ठीक है, चलिए छोड़ दीजिए, मैं कर दूंगा, मैं देख लूँगा। Okay, ठीक। Okay, so good afternoon everyone. So from today we will be starting fluid mechanics. Okay. Good afternoon. Good afternoon. I have got a lot of messages. Good afternoon messages. A lot of good afternoon messages. Very nice. Very nice. Be active. Okay. So from today we will be starting fluid mechanics. Okay. So regarding fluid mechanics. So as far as our branch chemical engineering is concerned, so out of the total technical subjects that are what we have, for example, we have 70 marks of technical subjects in GATE examination. So fluid mechanics, obviously we cannot predict that how much of fluid mechanics will be asked in examination, but still nearly 8 to 10 marks. Nearly 8 to 10 marks is fluid mechanics. Okay. Nearly 8 to 10 marks is fluid mechanics, but obviously this ratio is varying a lot. Okay, for example, this year IIT Bombay is setting the question paper. Okay, basically IIT Bombay is the governing authority. Okay, so it has the authority to choose questions. Okay, so obviously it depends upon the, you can say upon the weightage. It depends. The weightage also depends. So in some year the weightage is, you can say, very high. Some year the weightage is very less. Okay, but normally 8 to 10 marks is the FM, fluid mechanics part. Okay, so if you have any doubt, you can ask me. Okay, even you, if you have any doubt, you can ask me. Okay. So now regarding fluid mechanics, so we'll be starting the fluid mechanics. First of all, we'll be studying about the statics part. Okay, good afternoon. Okay, so first of all, we'll be studying about the statics part. Then we'll be going to the kinematics part, and then we'll be going to the dynamics part. Okay, so fluid mechanics has been characterized into various parts. So first one being the statics, then we have the kinematics part, then we have the dynamics part. Okay. So one by one we'll be discussing all these parts, and regarding all the students who are listening me for the very first time, I would like to tell you that whatever doubt you have, even if you have a single bit of doubt, because I'll be starting from a very zero level, very ground level, okay, I'll be assuming that you don't know anything in fluid mechanics. Okay, so I'll be starting with a very basic level. If you have any type of doubt, whether it is a very silly doubt or a very complicated doubt, you can ask me. Okay, so now let us start the fluid mechanics. Okay, so regarding fluid mechanics, so fluid mechanics. Now let us start with a very basic term regarding fluid, right? Fluid, and then we have mechanics. So first of all, let us discuss about fluids. Okay, so what is a fluid? If somebody asks you what is a fluid, so what is the layman, you can say, definition? The layman definition is a fluid is a substance or a material which can flow actually. So that is fluid. That is the basic, very basic definition of fluid. Okay, so what is fluid? Any substance that can flow, is termed to be as a fluid, and that is very basic, you can say, very basic definition of fluid mechanics. Okay, very basic definition of what a fluid is. Okay, sometimes the people, the students, sometimes if I ask them, so what define a fluid, and give it examples, so what they say is that any substance that can flow, for example water, oil, but they don't give the example of gases. Okay, and you know that fluids, it cannot just be only you can say liquid, it can also be gases. Okay, now I have written that can flow. That can flow. Now for example, I have a duster with me. Let us say I have a duster with me. Okay, I have a duster with me. If I tilt this duster, do you think that it will flow? Obviously it will not flow, because the intermolecular attraction between the, you can say, intermolecular forces are very high, so it will not flow automatically. But when I give you the example of, let us say I have water in glass. Okay, I have some water in glass, and if I tilt the water, you can see that after some time, if you keep changing the angle, after some time the fluid will come out of it. Why? Because the intermolecular forces are very less. The intermolecular attraction forces are very less. Okay, and these types of substances are known as fluids. So I can say that regarding flow, why does a particular, okay, good afternoon, okay, so why does a particular substance flow? Because due to weak intermolecular forces. Weak intermolecular forces. Due to weak intermolecular forces, a particular, you can say, substance, it flows. It can be a gas or it can be a liquid, right? So fluid, it can be a gas or it can be a liquid. It depends. It depends on the intensity of this intermolecular force. It depends on the intensity. Okay? In solids, the intermolecular forces are very high in solids, right? So that is why, if the intermolecular forces are very high, so that is why what happens is that they cannot flow on their own. They cannot flow on their own. Okay, so that is the, you can say, very layman or very basic definition of a fluid, what a fluid is. Now as far as mechanics is concerned, so what is mechanics? Now let's go to a very basic, you can say, definition of mechanics. So what is mechanics? So if, for example, again I am taking this duster as an example. Let us say that you have a duster like this, okay? If you apply some force on this duster, what will happen? If the friction is very less, it will move. If the friction is very high, it will not move, but shear stresses will be generated between the surface and the duster. So anything can happen. If it moves, either it will move with a velocity or with an acceleration. Okay, so the branch of science which deals with the study of effect of a particular force on a particular body, that is known as mechanics. Okay, that is known as mechanics. So mechanics, I can say that the branch of science which deals with studying the effects of force on a body. Okay, now the question is, sir, why are you just telling us what is fluid, what is mechanics? Why don't you just start with the, you can say, the exact topic that we have in fluid mechanics? My answer would be that, dear students, okay, even I know that you must be knowing what is fluid and what is mechanics, but when it comes to interviews, for example, you crack GATE examination with a very good rank, if you go to PSUs, they are asking very basic questions. As far as fluid mechanics is concerned, they are asking very basic questions. What is Pascal's law? What is fluid mechanics? What is this? What is that? What is kinematics? What is the difference between kinematics and kinetics? So they are asking very basic questions in PSUs. Okay, so that is why it is very important for us to know that what exactly is fluid mechanics. Clear? So why is fluid mechanics also called as momentum transfer? Don't worry about that. We will be studying what is momentum transfer when we will be discussing about gases. Now what is momentum transfer? Okay, because in case of our, you can say, in case of our gases, the main, you can say, the property of a fluid, in case of a gases, when we are discussing, we are mainly discussing with the momentum transfer. Don't worry about that, how the momentum gets transferred, don't worry. Okay, we'll be coming to that also. So we have to go step by step. We have to go step by step. Okay, so if I combine all these two, if I combine these two words, what I will be getting, to study the effects of force, to study the effects of force on a fluid particle, to study the effects of force on a fluid particle is generally characterized as, is generally known as the fluid mechanics. It's generally known as the fluid mechanics, right? Now, fluid mechanics is further divided into a lot of parts. So we have our fluid statics, then we have fluid dynamics, and now we have become so advanced that if you go for M.Tech, we have the compressible fluid dynamics also. Compressible fluid dynamics, CFD. Compressible fluid dynamics also in M.Tech. So we have become very advanced nowadays. But fluid mechanics is not a, you can say, not a recent subject. From the time from Archimedes, okay, we have been studying fluid mechanics from Pascal, Archimedes, okay. So it is a very old subject. But nowadays we have CFD also, compressible fluid dynamics in M.Tech. Okay. So fluid dynamics is very important, okay, as well as fluid statics. But if you know that what is statics, then only we can go to the dynamics part. Okay. Now let us start with the fluid mechanics. So we have discussed that what is fluid, okay, and what are the various forces will be acting on fluid. I will be telling you. We have the surface force, we have the gravitation or the body force, that will be discussing. Don't worry about that. Okay. So, okay sir, okay. So obviously I will not be able to read all the questions, okay. Just now I read this question. So why this fluid mechanics also called as the momentum transfer, that we will be discussing when we come to gases. Okay, if you have any question, that keep on typing, I will be reading the questions and giving you replies. Okay. So now, my foremost mantra is that whenever I start teaching, I would recommend that open your notebooks and keep writing and keep your hand, make your handwritten notes. Okay. So I will also recommend you to open your notebook and write the notes. Okay. Yeah. Okay, open the notebook and start from the fluid mechanics. Okay, it would be very better, it would be best if you make a new notebook for that, it would be best. Okay, yeah, correct. Okay, so fluid mechanics, because the question is, sir, why do I have to write, why do I have to make notes? Why can't I just study with the material that you provide? You can study that also. Nothing you can say, nothing wrong in that. But the thing is that what I believe is that the self-handwritten notes are the most, you can say, advantageous things. Okay, they are mostly, you can say, when you revise the fluid mechanics portion or any portion, any subject, if you have handwritten notes, then you can relate yourself with the lecture. Okay, sir was telling us this thing in the lecture, so you can relate yourself with the lecture. Okay, so it should be a handwritten note. Never rely on someone other's notes. Okay, because it is not a, you can say, semester classes that we just copy and we just pass in the semester. It is not someone else's, you can say, classes. Okay, so it is a GATE classes. Okay, so now let us start with the fluid mechanics part. Okay, so let us start with fluid mechanics. So now we'll be going to statics, then after that the kinematics part, and the last one is the dynamics part. Okay, then we'll be studying about the meters also, fluid meters. Okay, but now before telling you each and everything, let me first of all tell you that in fluid mechanics, we do a lot of differentiation and a lot of integration. If you remember, if you go to the boundary layer flow, okay, boundary layer analysis, when we go to the turbulent flow, okay, and when we go to, you can say, kinematics also, so we know we do a lot of integration and a lot of differentiation. Okay, but if I ask you a question, you do differentiation. For example, if mathematics is concerned, so if a function is continuous, then you can do the differentiation of that function. Remember our class 12th also, if a function is continuous, then only it can be differentiable. Okay, because at the ends you cannot do the differentiation. We know all these things in class 12, that if a function is continuous, then only it is differentiable. Now in fluid mechanics, In fluid mechanics, we are doing a lot of integration, a lot of differentiation. Now the question is how? It means that if in fluid mechanics I am doing a lot of integration, lot of differentiation, then I have to consider the fluid to be a continuous, the fluid to be continuous or a continuum. Okay, so I have to consider, this is note, right? Note. I have to consider fluid to be continuous distribution of mass, to be continuous distribution of mass, and that is also known as continuum, CONTINIUM. That is also known as continuum. So we have to assume that the fluid is a continuous distribution of mass. It means that the gaps between two fluid particles are very less. The gaps between two fluid particles are very less. That is what we consider in fluid mechanics. And that is how we can do a lot of differentiation, a lot of integration. Because why I am talking about this? Because this question is a PSU interview question. The question was like this. So a student was sitting in the interview. So the first question was asked to him was, so he was my student. So the first question was asked to him is that, define fluid. So he said that a proper substance, it can flow and this and that. Okay. The second thing was, so is there a gap between two fluid particles? He said that yes, obviously sir, there is some gap between two fluid particles. The third question was, in fluid mechanics we do a lot of integration, a lot of differentiation. You know the continuity equation also, it is also in the partial differentiation. Okay, but you can do differentiation only to a continuous function. So if there is gap between two fluid particles, how can I do the differentiation or integration? Okay, so what is the reason? So that reason is basically this continuum and a dimensionless number that is known as the Knudsen number. Knudsen number. Knudsen number is given by Ku. This Knudsen number. A dimensionless number, Knudsen number given by Ku. Because there is an interview question and similar type of questions can be there in GATE examination also. Okay. Now this Knudsen number is a dimensionless quantity. Now the question is, sir, what is this Knudsen number? So the Knudsen number is given by mean free path lambda divided by the characteristic length. Don't worry, I will be telling you what is lambda and what is L. Don't worry. So Knudsen number is given by lambda divided by L. Now the question is, sir, what is this lambda and what is this L? Now for example, let us say that I am considering a particular length of you can say some fluid is flowing. I am considering a particular length in the fluid mass flowing. Okay, so let us say that this length I am considering it as L. So whatever the size of the continuum I am considering, that is L. Clear? Now what is lambda? So inside this continuum we have fluid particles. It can be a gas, it can be a liquid. If we have fluid particles, okay. So now let us say that this is one fluid particle. This is another fluid particle. Okay. So this fluid particle, it gets collided with this particle. It will transfer its momentum to this particle. If you know the momentum equation class 12, that is m1 v1 is equals to m2 v2. It will transfer its momentum to this particle. Okay, so this particle will get collided with this particle, and after that it will again collide to some other particle. It will again collide to some other particle and again transfer some momentum. Okay, so this distance between two successive collisions is known as the characteristic length, or known as the mean free path. Mean free path, that is lambda, right? So lambda is the mean free path upon characteristic length. Characteristic length. That is the Knudsen number. And Knudsen number is a very frequent question in interviews. That what should be the value of Knudsen number? So to make it to be a continuum, and what should not be the value of Knudsen number? Okay. So if the value of Knudsen number Ku is less than 0.01, if the value of Knudsen number is less than 0.01, we consider that the particular system is in continuum. Is in continuum means this thing is in continuum. if the value of Knudsen number is less than 0.01, we consider that our system is in continuum. Continuum means I can do differentiation and integration. Simple. I can do differentiation and integration. That is continuum. Clear? Now, if the value of Knudsen number, it lies between 0.01 to 10. If the value of Knudsen number lies between 0.01 to 10, I will say that it is a slip flow. Slip flow. Now what is slip flow? Don't worry, I will be telling you what is a slip flow. Clear? If the value of Knudsen number is greater than 10, I will say that it is a free molecular flow. Free molecular flow. Free molecular flow. Now let us understand this. I told you that Knudsen number is given by mean free path upon the characteristic length. So this is the characteristic length which I am considering in a continuum. Clear? Now lambda upon L. So if Knudsen number is very small, so 0.01 is a very small number, right? If Knudsen number is less than 0.01, it means that this L is very large, characteristic strength is very, or this lambda is very small. So if lambda is very small, it means that the distance between two fluid particles is very small. Clear? The distance between two fluid particles is very small. If the distance between two fluid particles is very small, what I told you that we consider to be a continuous distribution of mass. We consider to be a continuous distribution of mass. So in fluid mechanics, okay, slip and free molecular flow. Okay, don't worry, I'll be coming to that also. Don't worry, okay. So if Knudsen number is less than 0.01, it is known as a continuum. Okay. So now in fluid mechanics, whatever we will be studying, whether it is kinematics, whether it is dynamics, whether it is statics, whether it is, you can say, boundary layer flow, anything, whatever we will be studying, we will be assuming that the Knudsen number is less than 0.01. Now somebody asked me, sir, what does it mean, the slip flow, the free molecular flow? So let me tell you that when this Knudsen number is less than 0.01, when this Knudsen number is less than 0.01, now what happens now? Let me tell you. So if, okay, now let me rub this, the upper portion. Okay, now let me explain you what will happen if this is this and this is, okay. Now let me explain you. I hope that you have noted down. Keep making notes, okay, keep making notes side by side. Then I will rub it. Okay, what is the length called, the characteristic length? Okay. Okay, so one question is why this length is called as the characteristic length. So when I will be coming to the Reynolds experiment, so when will we go to the Reynolds experiment, right? It is a dye experiment, Reynolds dye experiment, okay, with the help of which Reynolds told us that this should be the Reynolds number for to be a laminar flow and to be a turbulent flow. Then I will be telling you in detail what is this characteristic length. Okay, but till that time being, just remember this thing, that whatever the length we are considering, considered to be characteristic length. But when will we go into the Reynolds experiment, the dye experiment of Reynolds, okay, and then after that we had the Prandtl experiment, then I will be telling you in detail what is this characteristic length. Don't worry, okay, because everything has a time, okay. So what are this slip and free molecular flow? I will be telling you. So what is valid for momentum in solids, it will hold good for liquid also. Okay, so regarding the momentum transfer, is it momentum transfer? So is it valid for in solids or, okay, so regarding the momentum transfer, let me tell you that whatever we are studying, that regarding the momentum transfer, it will be basically valid for gases as well as liquids. In gases, the momentum transfer is very high because gases, they collide with a lot of velocity, even though the mass is very small, but they collide with a lot of velocity, so they transfer a lot of momentum. As far as the liquids are concerned, they have some mass, but the velocity is not high between two particles as well. The distance is also very small, so that is why the property of this you can say liquid, it is not because of the you can say molecular transfer, but because of the hydrogen bonds, if water is being used, or because of the intermolecular force, because they are very close to each other. We are very close to each other, but gases molecules are very far from each other. So the main property is, because intermolecular forces will be very small if they are very far from each other, but then when they will collide, then they will constitute the momentum transfer. Okay, now let me go to the question number 2. Sir, what is the slip and free molecular flow? Now let me tell you what is this slip and free molecular flow. Okay, now let me rub this. Okay, now when this Knudsen number is less than 0.01, we consider it to a continuum. If a particular fluid, whether it is a gas or whether it is a liquid, it is in a continuum, then what will happen? Now first thing is that we can do integration and differentiation. That is the first thing. The next advantage is that, for example, you have a surface like this. For example, you have a surface like this. When particles will come, when the fluid particles will come, for the time being, let it be liquid. For the time being, let it be liquid. Okay. When the fluid particles will come, the particles which are near to the surface, what will happen is that they will stick to the surface. They will stick to the surface. If I am considering it to be a continuum, and if I move in the y direction, so here the particle velocity is 0. Here the particle velocity is 0, but as I am moving in the y direction, so what is happening is that the particle velocity will slowly it will increase. And after some time, after some distance, after the boundary layer, it will become equal to the stream velocity. At u is equal to u infinite, that is the stream velocity after some distance. That is known as the boundary layer. We will be coming to that, don't worry. If the Knudsen number is in between 0.01 to 10, then what will happen? Then what will happen is that if fluid is coming from this direction, so this fluid will not stick to the surface. It will not stick to the surface. It will slip. Because why it will slip? Because the gap between two particles is very large. So the force of attraction, if the gap keep on increasing, the force of attraction will keep on decreasing. Okay, and these two particles, because the force of attraction is very less, will not hold each other. So each and every particle will behave as an independent particle. And it will slip. The moment it comes to in contact with the surface, it will slip. That is why it is known as a slip flow, and that is a free molecular flow. So free molecular flow, generally we've seen gases. Free molecular flow, right? So one particle is going here, one particle is going there, one particle is going there. So that is a free molecule, because the gap between two particles is very large. If the gap between two particles is very large, what will happen? The force of attraction will be small. Because you know that from the, we know that the force between two particles, it is inversely proportional to the, you can say, distance square, if you remember. Clear? So if the distance is very small, then the force will be very high. Okay. So force is inversely proportional to distance square between two particles. If the distance is very small, force between two particles will be very high. So in fluid mechanics, whatever we'll be studying, whether it is kinematics, whether it is dynamics, whether it is turbulent flow, whether it is, you can say, static flow, whatever we'll be studying, we will be assuming that the Knudsen number is less than 0.01. Okay, we will not be considering the slip flow, as well as we will not be considering the free molecular flow. We will be considering that a Knudsen number is less than 0.01. And that is an interview question, not a gate question. In gate examination, questions have not been asked from the Knudsen number, but in interviews, questions have been asked. Okay, so that is the dimensionless quantity, that is the Knudsen number. So note it down, then we will proceed. Sir, how the values of range between we fixed? Okay, so the range has been fixed by experiments by the scientist at the Knudsen. Okay, so he performed some experiments in the laboratory and he fixed these values, that if the mean characteristic length, the ratio of the, you can say, the characteristic length and the mean free path is less than, you can say, 0.01, then he said that it is a continuum. Okay, and after that, and these ranges have been already been fixed by certain experiments. Okay. Sir, why the length is called the characteristic length? I will be clearing that in the Reynolds experiment. Sir, what are these slip? Okay, I have done. Sir, but is it valid for, okay, this I have cleared. Okay, sir. Okay. Can flow of mercury be an example of a slip flow? No, mercury cannot be an example of a slip flow. Why? Because in mercury, okay, I am telling you that it will slip. Like for example, this is a, you can say, a base. So if you put mercury here, so the mercury will stick to the surface here, right? Okay, but the upper portion of the mercury, because it wants to be in less contact with the surface, so it is a non-wetting liquid. I will be giving you example of non-wetting liquid. So it will try to, you can say, it will try to be like this. It will try to have the minimum contact with the surface, right? But as far as this is concerned, there will be some movement, you can say, some force of attraction between the surface and the you can say mercury. Obviously the area of contact will be very small, but still there will be some force of attraction between the two particles. But as far as this is concerned, if you apply some shear stress to mercury, it will behave like this. If you apply some shear stress to mercury, so we cannot say that the you can say this slip flow is valid for mercury. We cannot say that. Okay. Sir, is it possible? Okay, sir, is it possible to measure mean free path as it is a microscopic parameter? Yeah, obviously it is possible. It is very difficult. Okay, so please explain slip flow again. Okay, now let me explain the slip flow again. And another question is, sir, is it possible to measure the characteristic length, because it is a microscopic? Obviously, two particles are very small. So we have a lot of, you can say, methods to determine the mean free, determine the characteristic length or the mean free path. The first method is the momentum transfer. So with the help of the momentum transfer, how much energy has been lost by a particular molecule, with the help of that we can determine what is the characteristic length and what is the mean free path. We can determine all these things. Okay. The next question is that, sir, please explain slip flow. Okay, please explain slip flow again. Now let me explain the slip flow again. Okay. Now if the Knudsen number is in between 0.01 to 10, then what will happen? What will happen is that we know that the Knudsen number is lambda upon L. We know that Knudsen number is lambda upon L. If the value of Knudsen number is increasing, it means that the mean free path is increasing. Now it has become like this. So these are the three particles. So this is the mean free path, lambda. Now it has increased. Okay, it has increased. Okay, and this has, for a small continuum, for a small space, for a small characteristic length, this has increased. It means that the force of attraction between two particles is less as compared to this case. It means that the force between two particles is less as compared to this case. Now what will happen is that, for example, this is a surface. If fluid is coming from this direction, so what will happen? Let us say these are the two particles. So the force of attraction between the two particles is smaller as compared to this case. So what will happen when this particle will collide with the surface? This particle, because the force of attraction is small, will not allow this particle to stick to the surface, because the force of attraction is small. So what will happen? This will happen. So after some time, it will happen like this. So this is going like this. So it will not stick to the surface, it will slip to the surface. Okay, so that is the slip flow. So we are not studying the slip flow as well as the free molecular flow. So in fluid mechanics, we will be restricting ourselves to the Knudsen number less than 0.01. Clear? Less than 0.01. Now let's proceed. We don't have to do PhD in Knudsen number. Don't worry about that. Okay? We don't have to do PhD in Knudsen number. Just remember this thing, if the Knudsen number is less than 0.01, the voids are negligible. The voids are minimum, very less voids, negligible voids between particles. Okay, shall I rub this? Okay, I am rubbing this, okay? I am rubbing this. Okay, I am rubbing this, okay? Okay, let me rub this, okay? Okay. Now, let us discuss about the types of forces acting on a fluid particle. Okay. So, for example, let us say I am standing here. So, I am standing here. So, what are the various forces acting on me? So, first force will be, because, for example, I am standing here. So, above me I have atmosphere, right? Above me I have a troposphere, stratosphere, okay? And that atmosphere, it is putting a pressure on my surface. That pressure is perpendicular to my surface, and that is known as the atmospheric pressure. Clear? Another force which my body has is my weight. So my weight, due to the acceleration due to gravity, my weight is acting, you can say, towards the, you can say, core of the earth, due to the acceleration due to gravity. That is the weight. So any particle, whether it is a fluid particle or any body, it has two types of forces acting. So types of forces. Types of forces acting on a fluid particle. Clear? So the first force is a, you can say, body force or surface force. First of all, surface force. Second one is a body force. Body force. Can we say that the free molecular flow is close to the real flow condition and continuum is an ideal condition? So we cannot say that continuum is an ideal condition, because continuum happens in case of a liquid flowing. But we can say that the free molecular flow, you can say that it can be in the case of gases. It can be in the case of gases, we can say that the free molecular flow is taking place. But as far as the liquid is concerned, which have very high density, okay, because water also has very high density, 1000 kilogram per meter cube. So we can consider that liquids have this, you can say, this flow, a non-slip flow, right? Which can we say that the molecular flow is close to the real flow condition and continuum flow. Yeah, continuum flow, it can be in the case of our liquids, okay, and the free molecular flow, it can be in case of our gases. It can be in case of gases. We can say that. Okay, so types of force acting on a fluid particle. So first of all, it can be a surface force, and second, it can be a body force. Okay, body force. So the force is acting on the surface. For example, I was giving you my example. For example, I am standing. So atmospheric pressure is acting on my body, and that would be perpendicular to my surface of my body. Okay, so it will be perpendicular. Okay, so atmospheric pressure is acting, and if I am standing, my weight is also acting. Okay, so you can say that body forces are due to the gravitational force. Gravitational force. Due to the gravitational forces, okay, that is the body forces. Okay, so in surface surface force, the most important example being, or the most prominent example being, the surface tension, and in body force, the weight of a particular flow, the weight of a particular body, it comes under the body force. Clear? So we can say that. Okay. Now, why are we telling you, or why am you telling you all these things, the types of forces acting? Because whatever we'll be studying in statics, okay, while we'll be discussing about the statics, so we'll be dealing with a lot of surface forces, okay, and a body forces also. Clear? So that is a surface force acting on the surface. So surface force can be surface tension, it can be adhesion, it can be cohesion, etc. etc. And body force being gravitational force due to, it can be weight of a body. The example can be weight of a body. The example can be weight of a body. Okay? And I hope that you know the difference between mass and weight. Do you know the difference between mass and weight? What is the difference between mass and weight? What do you think? Even if you tell me that wrong, it doesn't matter, because we are here to increase our concepts. What do you think? The difference?
Weight is measured in kilogram.
Weight is measured in kilogram, and mass, Newton?
Mass is measured in Newton meter per.
90. Okay, don't worry. Okay, so I hope that you must be knowing the difference between mass and weight. Even if you don't know, don't worry at all. Okay, because now what is mass? So mass basically tells you about the quantity of matter in it. For example, my weight is 90 kgs. My weight is 90 kg. So this is not my mass. So this is what my, you can say body, how much force my body is exerting on earth, right? It is actually not kilogram, it should be kilogram force. But generally what we do is that we say that it is kilograms. Okay, it should be kilogram force, not kilograms. Okay, so what is the difference between, you can say, mass and weight? Mass and weight. So mass actually tells me about the quantity of matter. Quantity of matter. It actually tells me about the quantity of matter. And what about weight? It tells me how much that quantity of matter is exerting force on earth due to the acceleration, due to gravity, because there will be some weight of the, you can say, a body, right, due to acceleration, due to gravity. So it tells me about the force. About force. It tells me about the force. And it tells me about the quantity of matter. It tells me about the quantity of matter. Yes, clear. You can say that. You can say that. You can say that. You can say that. Acting on the surface. Okay. So we have one more question. The question is, mass is a matter content and weight is a force. Okay. Can we say viscosity is also a surface force? Viscosity is not a force. Viscosity is a property. Viscosity is not a force. Some shear force will be acting. Some shear force will be acting on the surface, but viscosity is not a force. Viscosity is the property. Viscosity is not the force. Don't worry, we'll be coming to that also. Viscosity, okay? Viscosity is not a force. Viscosity is a property. So very simple, okay? So mass and weight, okay? Now let us move forward. To the properties of fluids. Okay? Now let us move forward to the properties of fluids. So these are the two types of forces acting. First one is the surface force and we have the body force. Okay? Till now that is more than sufficient. But when we going, you can say, more deep into the concepts, then we will be elaborating all these concepts. Okay? So now let us understand about the properties of fluids. Okay? Let me rub this. Properties of a fluid. Properties of a fluid. The first property is the density or mass density. Mass density. Density or mass density. If anybody asks you what is density or mass density, you will say that, sir, we know that density is given by rho and density is equals to mass per unit volume. That is the layman thing that we know. But the question is, sir, what actually density is? Now, density actually tells you about the compactness. Density actually tells you about the compactness of a body. Now, for example, I have this duster with me. It has some density. So I can say that if it has a very high density, then the particles will be compacted together in a very small volume. Okay, so if somebody says that a particular thing has a very high density, for example, mercury has very high density, 13.6 times the water, I will say that the particles in a particular volume, in case of a mercury, they have been 13.6 times closer as compared to water. Right? So basically, density or the mass density tells you about the compactness. If somebody says you what is the physical significance of density, tell him or her that it tells you about the compactness. It tells you about the compactness. Okay? So it is kilograms per meter cube. Kilograms per meter cube. So the unit of mass is kilogram. Although what we measure is that we say that it is actually you can say I am 95 kg, I am 100 kg. That should be kilogram force, because the unit will come out to be equal. The unit of mass is also kilogram and the weight is also kilogram, weight which we are measuring in India, right? 95 kgs, I am 66 kgs and so on, right? So the unit of weight should be kilogram force or Newton. Okay, so kilograms per meter cube is the SI unit. SI unit. If you go to the dimensional analysis, it is ml minus 3 T0. That is dimension. I hope that you know that what is m, what is l, and what is t. So m stands for mass, l stands for length, and t stands for time. When we'll be discussing about the dimensional analysis and similitude, and there I will be telling you all these things. Okay, Buckingham pi theorem also we have. Okay, we have the Rayleigh's theorem also. We will be discussing that in detail there. Okay, don't have to worry. Clear? So mass per unit volume. Second thing is that we have the weight density. Weight density, or it is also known as a specific weight. Specific weight. Specific weight denoted by gamma. Weight density or specific weight denoted by gamma. Okay, so gamma is equals to weight per unit volume. Per unit volume. And what is weight? Weight is the force exerted by a mass on the surface due to the acceleration due to gravity. So can I say that weight is equals to mass into acceleration due to gravity? We already know this, right? And divided by the volume. Clear? And mass into acceleration due to gravity, we say that it is Newton or kilogram force. Newton divided by meter cube is the SI unit. Clear? Note it down, then we will proceed. I hope that you are getting. Okay, can we say okay, sir? I hope that you are getting. Okay, I have started with a very zero level. Okay, So that because a lot of students they face a lot of problems in the boundary layer flow, okay, in the boundary layer flow, the pressure analysis. The recently after 2016 in our chemical, a new topic has been added, that is the turbulent flow, velocity profile, turbulent flow. So a lot of students face a lot of problems there. So that is why I have started with a very basic level, very zero level. Clear? So that if you have any doubt, you can ask. Okay? Clear? Yes, sir. Yes, sir. Okay. So, regarding the mass density, so the mass density of water is very important, although it is generally given to in question also, but you should remember that the mass density of water is rho of water is 1000 kilogram per meter cube. 1000 kilogram per meter cube. Simple. Clear? Regarding this, you multiply this with 9.81, you will be getting nearly 9810, okay, 9810 Newton per meter cube, divided 1000 will be getting nearly 9.81 kilonewton per meter cube. That is the gamma of water. Clear? So at least for water it should be learned. Okay? Water you should remember 1000, very simple 1000, right? 1000 kilogram per meter cube or 9.81 kilometer per meter. At least for water you should remember. Okay? So now let's move forward to the third property of fluid, and that is known as the specific gravity or the specific density also. So a specific gravity. And you can determine the dimension also. For force it is mLT minus 2 divided by L cube. You can get the dimensional also. Even if you don't get the dimension, don't worry. When we going to the dimensional analysis and similitude, I will be telling you how to form the dimensional formula also, how to do the dimensional analysis. Don't worry about that. But if you know, we know that mLT minus 2 divided by L cube. So you will be getting mL minus 2 into T minus 2. You can get the values. Okay. So now, the third property is the specific gravity. Generally denoted by S, in some books G also. Okay. Regarding books. So students ask me, sir, which book should I prefer? Which book should I prefer? Okay. So I tell them that whatever I will be teaching you, more than enough. If you keep making notes, if you keep solving numericals, which I will be telling you, that will be more than sufficient. But still, if you want to refer some books, you can refer Fluid Mechanics by White. It has a lot of, in detail, it has a lot of theory is there, right? Okay. But obviously we are mainly restricting ourselves to the, you can say, the competitive point of view is concerned. So whatever I will be telling you, more than sufficient. And for numerical purpose, if you want to solve, so previous year gate numericals plus the material that which we will be providing will be more than sufficient. But still, if you want some questions to solve on your own, you can refer either D.S. Kumar or you can refer to R.K. Bansal also. In R.K. Bansal, fluid machinery is also given. That is not of our concern. Okay. So R.K. Bansal, D.S. Kumar for solving numericals, and for concept it can be White. FM, Fluid Mechanics by White. Otherwise, whatever book you are referring to, that is be more than sufficient. Plus, whatever I will be teaching you, keep making notes and keep practicing. You will be able to solve any question coming in gate examination. Clear? Now let's move to specific gravity. To understand you what is specific gravity, now let me tell you one thing. Let us say that I have these two dusters with me. Okay, so one is a heavier. This is a wooden duster. This is a wooden duster. It seems to be heavier. It seems to be heavier. And this is a very plastic duster. It seems to be very light. Okay, so if I have a bucket full of water, if I drop these two dusters, what do you think? Which duster will sink and which duster will float? Obviously, until and unless I don't tell you densities, you cannot say that which will sink and which will flow. But let me tell you that the density of this duster is, let us say, it is 2000 kilograms per meter cube. Let us say mass density is 2000 kilogram per meter cube. And for it is plastic duster, it is, let us say, 823 kilograms per meter cube. Then what do you think? Obviously, the particular duster with a higher density, if you drop it in water, it will sink. That is the common sense that we are using. Okay, for example, if you have a stone, if you drop it in water, it will sink. Why? Because the density of that particular material is very high. And to measure this thing, whether something will sink or whether something will not sink, there is a term which is known as the specific gravity or relative density also. That is also a relative density also. Clear? Specific gravity is generally used. Specific gravity is generally used. So what we can say that this specific gravity is equal to the density, mass density or weight density, whatever you want, because Gg will get cancelled out. I will be telling you, don't worry. So it is the density of any liquid or any fluid with respect to density of a standard fluid. Density of standard fluid. Density of standard fluid. Clear? In case of liquids, the standard fluid is taken as water. In case of liquids, the standard fluid is taken as water. So can I write it like this? That density of any fluid divided by the density of water. The density of water, right? And what is the density of water? The density of water is 1000 kilograms per meter cube at 4 degrees Celsius. That is the exact, you can say, exact definition of density. If somebody asks you what is the density of water, don't just tell him that it is 1000 kilograms per meter cube. You tell him 1000 kilogram per meter cube at 4 degrees Celsius. Because the volume of water keeps on changing, but at 4 degrees Celsius it has the highest hydrogen bonds, right? And the density is found to be 1000 kilogram per meter cube. But if you increase the temperature, decrease the temperature, it will change. It will change. Clear? So that is 1000 kilogram per meter cube at 4 degrees Celsius. That is the standard. Similarly, it can be for gamma also. So gamma of any substance divided by gamma of water. Why? Because if you multiply it with G and divide it with G, it will become gamma. So same one, the same thing. G will get cancelled out. It will be the same thing. Clear? आ रहा समझ आपको? Clear? Now, this was regarding liquids. The standard fluid is taken as water. But as far as air is concerned, as far as you can say gases are concerned, the standard fluid is taken as air at, let me tell you, specific gravity is equals to density of, you can say gas, any gas, divided by density of air at STP. STP means standard temperature and pressure. Standard temperature and pressure. And at STP, the density of air is taken as 1.21 kilogram per meter cube. 1.21 kilograms per meter cube is the density of air is taken as at STP, standard temperature and pressure. That is 1.21 kilogram per meter cube. But for fluid mechanics, obviously we will not be going in detail in for the you can say gases. So we will be restricting ourselves to liquids only for fluid mechanics. Clear? As far as the gate point of view is concerned, we will be restricting ourselves to liquids only. Clear? So What should be remembered? So only one thing should be remembered, that will be used in manometers. So what is the manometer? Don't worry, I'll be teaching that. So for mercury, this is specific gravity, or that also known as the relative density also, it is actually taken as 13.6. For mercury, the specific gravity is taken as 13.6. It means that if I put it in this equation, I will be getting 13.6 is equals to density of mercury divided by density of water at 4 degrees Celsius, and that is equal to density of mercury divided by 1000 kilograms per meter cube. So density of mercury will be 13.6 into 10 raised to the power 3 kilogram per meter cube. So for density, it should be remembered to you, because it will be frequently used in manometers. Clear? Higher will sink. Okay. Okay, so people are also asking me regarding books. So buoyancy of surface body, okay, Eunice, okay. Yeah, Senegal, you can also refer to this book also. That is also, as I have told you, no book is bad and no book is good. Whatever I have told you here, it is my experience. Okay. So no book is bad, no book is good. You can refer any book. If you are referring some book when you were in semesters, you can refer that book also. Does not matter. Your concept should be clear. You can refer any book. Whatever the name you have given to me, although I have not read this book, but I have heard that this is a very good book. Obviously, I have not read this book. I have read White, D.S. Kumar and R.K. Bansal. That is why I can say that okay, these are the good books you can refer to. But this book, regarding this book also, I have heard that this is also a very good book. Okay, you can also refer that book also if you want. Okay, so no book is a bad book, no book is a good book. Okay, the only thing is that the approach is different. In some books, you will find theory in a lot of details. In some books, you will find very less theory, but you will find a variety of numericals. Clear? So every book has its own advantages and own disadvantages. So for example, I was talking about R.K. Bansal and D.S. Kumar. Theory is not very much, but quality of numerical, the variety of numerical is very large. As far as White is concerned, the solved examples are very less, but as far as the theory is concerned, theory is very good. Okay, so you can refer any book you want. Doesn't matter. Yeah. Okay, note it down, then we'll proceed. Clear? The next property is known as the specific volume. Because why I have told you about the specific gravity? Because when we'll be solving some numericals, in those numericals you will not be given the mass density of a mercury or some other material. You will be given specific gravity. At that time, don't get confused that some mass density is not given, how to calculate the mass density. Because specific gravity is given to you, you can directly calculate the mass density. Simple. Okay? Now, fourth property is the specific volume. And specific gravity is dimensionless. Because we are dividing same quantity with the same quantity. That is, we are dividing density with density. So whatever the unit density had, it has been divided by density. It is a dimensionless quantity. So this is also a gate question which is coming. So some you can say quantities will be given to you on the left hand side, and on the right hand side you have to match which one is the dimensionless quantity. So generally Reynolds number is given, Froude number is given, Mach number is given, specific gravity is given. So you know that Reynolds number is also a dimensionless quantity, as well as this specific gravity is also dimensionless quantity. So these questions are very frequently asked in examination. Clear? The next property is, I guess it is fourth, right? I guess it is fourth one. Specific volume. Specific volume. Right? Specific volume. So specific volume, it is actually equal to volume per unit mass. Volume per unit mass is termed as the specific volume. Now the question is, sir, will it be used somewhere? Actually, in examinations, very small question, 1 mark questions have been asked that you determine the dimensional formula of specific volume. At that time, if you don't know what is specific volume, you will not be able to form the dimensional formula. So specific volume is given by volume upon mass, that is 1 upon rho is specific volume. The specific volume. 1 upon rho is the specific volume. Okay? So very small questions, 1 mark questions, the dimensional formula for specific volume is. So if you don't know what is specific volume, you will not be able to determine the dimensional formula. Clear? So it is 1 upon rho. Now fifth property of fluid is known as surface tension. Now this has to be discussed. Surface tension. Surface tension. Now listen to this very carefully. Okay, how this surface tension it gets formed. Okay, how it gets formed. Okay, so it is a very conceptual thing how it gets formed. If somebody asks you what is surface tension, you say that the surface, it acts like a membrane. Okay, you must be knowing all these things. It acts like a membrane. You must be giving some examples. If somebody jumps in a swimming pool, the water is at rest. If somebody jumps in a swimming pool with the highest surface area, either his bones will be broken or something will happen, because there is surface tension on the surface of, you can say, fluid, and that will act as a reactive force if somebody is jumping in a swimming pool with a higher surface area. Okay, that is why we always jump like this in a swimming pool, right? To minimize the surface area. Okay, we do not jump straight away. Okay, so the reason being surface tension. Now how does it actually happen? Now let me tell you that, let us say that we have a container. And this container is full of fluid. For the time being, let us say it is water. This container is full of water. Clear? This container is full of water. Now just imagine that one particle is here, one particle is here, one particle is here. We have a lot of fluid particles, and some particles are at the surface also. Now let me consider 3 particles, 1, 2 and the surface particle. Now let me consider only 3 particles. One is the surface particle and 2 particles are here, let us say. If I consider these particles, so we have force of adhesion and cohesion. I'll be telling you what is adhesion, what is cohesion, but for the time being, just know one thing: the adhesion is the force of attraction between 2 different media. One media is, you can say, this water, and one media is the glass surface. So that is the adhesion. Cohesion. Co means corporation. CO means same material or same substance or same particle. So the force of attraction between the same particle is known as cohesion. So if I consider these 2 particles, one is inside the container and another one is on the surface of the container. So what type of forces will be acting on this particle? So the one force will be, there will be one particle, there will be one particle. So from every direction, forces will be acting on these 2 particles. This particle also, same force will be acting on all the directions. Force of cohesion will be acting like this. Clear? But when I look at this particle which is at the surface, what will happen? So one force will be acting on this side, one force will be acting on this side, some forces will be acting like this. So you can see that the particle which is at the surface, no force is acting, you can say, in this, which is under the atmosphere. This is atmosphere, which is in contact with the atmosphere. No such force is acting, no such cohesive force is acting. Clear? So what will happen is that you can see that the resultant forces in particle A and particle B are zero. The resultant forces are zero. So I will say that these particles are stable. But as far as this particle is concerned, which is at the surface, so some forces acting here, it will get cancelled out. But these forces must be having some resultant. These forces must be having some resultant R. And that is not being balanced. So you can see that if I have a container full of water, so on the surface every particle has some force, has some resultant force inside it. So what will happen if it is a wetting liquid? Now what is wetting liquid? I will be coming to that also. If it is a wetting liquid, so there will be a stretched membrane type of membrane will be formed at the surface, because every particle is being you can say pulled inside with a resultant R. So there will be a membrane type of thing will be happening. So it will be stretched membrane. Clear? And that stretched membrane is known as the surface tension. Clear? And it is measured per unit length. So on whatever surface it is acting, you can say the total length of the surface is actually measured along the surface. Clear? So surface tension, it is actually measured, the force per unit length is actually the surface tension. That is surface tension. Clear? Now what are wetting liquids and non-wetting liquids? Because I was explaining you this. Now what are wetting liquids and what are non-wetting liquids? Non-wetting liquids. What are wetting liquids and non-wetting liquids? Okay, so any question? Okay, noted. Okay, clear. Oh, are you getting it?
Yes.
Are you making notes? Okay, if I give you numericals, will you be able to solve? हो जाएगा? होगा? ठीक. Oh, what's your name? I forgot your name. Gaurav. Okay. Okay, great, right? So wetting liquids and non-wetting liquids. Now wetting liquids, as from the name it is clear, it will wet something, right? So wet means it will wet the surface. Now why this wetting liquids happen? If the force of adhesion is greater than the force of cohesion, we say that it is a wetting liquid. Why? Because if the force of adhesion, now let me again draw this container. Now these are the fluid particles. Now if the force of adhesion is greater than the force of cohesion, adhesion between the water and between the surface or this glass surface or this container surface, if it is high, what will happen? The water will try to stick to the surface. And will try to cover the maximum area. Clear? So these types of liquids are known as the wetting liquids, because they will try to cover the maximum area of the container and they will try to wet the container. That is why these are known as the wetting liquid. For example, water. We have non-wetting liquids also. The example being mercury. Clear? So what is happening is the force of cohesion. The force of cohesion is greater than the force of adhesion. The force of cohesion is greater than the force of adhesion. So what is happening is that the intermolecular forces are very high as compared to the forces between other two different media. For example, if I have mercury here in this tumbler, so the forces between the particles are very high as compared to this mercury and this surface. So it will try to have the minimum area of contact. That is why I was telling you that, for example, we have a surface like this. If you drop some mercury over here, it will try to have the minimum area of contact. It will try to have the minimum area of contact like this. But as far as the water is concerned, so water It will try to have maximum area. If you try to pour some water, the water molecules will be like this. So this is the angle of contact, theta. It is acute, and this is the angle of contact, this. So you can say it is obtuse, right? Okay. So you can say that this angle is obtuse, or very great angle. We'll be coming to that also. I'll be talking about the capillary action. We'll be coming to that also. Clear? So for wetting liquid, contact angle is less than, yeah, correct. Acute angle, correct. Correct. Clear? So one question is also there. Please repeat last part, sir. Okay, I will repeat. Okay. So in case of surface tension, why are we considering the top surface? Why don't we consider the bottom surface, and the why don't we consider the bottom most surface? Okay. So because as from the name it is clear, surface tension. Okay. For example, as far as the bottom particles are concerned, for example, a particle is there at the bottom. At this bottom. So it will have some force. It will have some force of adhesion. It will have some force of cohesion also. So here also it will be 0, because here it has some adhesion. It has some adhesion with the, you can say with the it has some adhesion with the surface. But as far as this is concerned, as far as the top is concerned, there is no adhesion, because there is no such media above it. If this container would have been covered by the same media, there would not have been any surface tension. If there would have been no air above it and it have been a covered container, there would have been no surface tension. But as it has not been covered, above it we have, you can say above it we have air, and the resultant is not being balanced, we will certainly have some surface tension. Okay. So please repeat the last part. Okay, last part, which part? Okay, wetting and non-wetting. Okay, now let me repeat about the wetting and non-wetting liquid. Okay, so what are wetting liquid? In which the adhesive forces or the force of adhesion are greater than the force of cohesion. Now let me give you one example. So let me take this example. Yeah, only this example. Okay, now for example, this is some fluid, okay, this is some surface, okay. If the force of attraction between this surface and this fluid is very high, if the force of attraction between this is a surface and this is some fluid, it can be oil, it can be water, anything, if the force of attraction will be very high, so even if you try to, you can say apply some shear forces, it will not try to move, because the force of adhesion between these two particles is very high. So it will try to cover the maximum area. And hence these types of fluids are known as the wetting fluids. But as far as your non-wetting liquids are concerned, so the force of cohesion, that is the force between my hand molecules or hand particles, are very high as compared to this. So I will try to have the minimum area. I will try to go to my friends. Who are my friends? My friends are my particles which have close contact with me, which have close bond with me. So I will go to my friends. Okay, so you can also, you can say, understand with that example also. This is your friend, okay, and this is your friend, and this is your best friend. So obviously you will try to spend maximum time with your friend. And if this is not your friend, if your friends are living in the vicinity of your house, so you will try to spend maximum time with your friends which are in the vicinity of your house, not with some other friends. You can understand in that way also. Wetting and non-wetting liquids. Sir, can paint be an example of a wetting liquid? Depending on which type of paint it is. depending on which type of paint it is. Okay, so some paints, for example, there are some paints which are basically used for the wall painting. That can be an example of a you can say wetting liquid, because it tries to cover the maximum area. But there are some paints which are used for the corrosion resistance, some other type of things. So it depends on the type of paint. So I cannot say that paint can be an example of a wetting liquid or not. It will depend on the type of paint. It will depend on the type of paint. Okay. Clear? So that is the surface tension. Now in the surface tension we have one more term. In the surface tension we have one more term that is known as the surface energy. That is known as the surface energy. Okay, let me rub this. Let me rub this. Let me rub this. Okay, so the question is, so one example of non-wetting fluid. One example of non-wetting fluid. So for wetting fluid we can have many examples. Water also I gave the example. Milk can also be example. Okay. Regarding the non-wetting fluid, blood can be an example. But depending on the surface on which it is, blood can be an example of a non-wetting fluid. Okay. Can you please explain the angles? Hydrophilic nature. Can non-wetting liquid with a okay, so don't confuse hydrophilic and hydrophobic with the non-wetting and wetting. I am talking about a surface, and that surface is not of water. That is you can say a metallic surface, or you can say or any surface. Okay, but if this would have been water, then you have the concept of hydrophilic and hydrophobic. Hydro means water; it is related to water. So, for example, if you have any substance, if you put in water, it will not try to form any bond with water. So that is regarding water. So don't confuse hydrophilic, hydrophobic with the wetting and non-wetting. Yes, Mercury. Can we relate with No. So can you please explain the angles of contact again? I will be explaining you the angles of contact when we will be discussing about the capillary action. There I will be talking about the angles of contact in detail. Don't worry about that. Okay. So now the next point here in the surface tension is the surface energy. Is the surface energy. Now what is surface energy? In the surface tension itself we have a topic that is known as surface energy. Surface energy, SE, surface energy. Now what is surface energy? Just now I have told you that there can be two type of liquids. One can be a wetting liquid, another can be a non-wetting liquid. Okay. Let me take example of a wetting liquid. Let me take example of wetting liquid, for example being water. Okay. Now if I take example of water, this is a container. This container has some water. Let us say up to this level it has some water. Up to this level it has some water. Okay. And you can see that there is a resultant force acting downwards on the surface. There is some resultant force acting downwards. Just imagine, okay, we have a water, let's say it's a round water container, and on the surface we have some resultant acting downwards. What will happen? Will the level of this water, will it be straight? It will not be straight. Obviously, everything tries to balance itself. So what will happen? The shape of this surface, it will become like this. If it is a wetting liquid, it will become like this. The shape of this surface will become like this, because every molecule has some resultant downwards. Try to just think it. Clear? Now if you look it from the top view, if it is a circular cylinder, it is a circular bucket, what will happen is that earlier the water was at this level, but as it has gone some here, so there is some difference. Earlier the water was here, but it has been stretched due to this resultant force. So the level of the water, it will have some change. Earlier it was here, now it is here. It has some change. If you look at from the top view, you can see that, okay, there is some change. There is some change. Clear? Now, some force is also acting. There is some change also. So, can I say that to form this shape, the surface tension has, you can say, this surface has some energy also. Because if you have force, if you have at some distance also, it has traveled, then can I say that some work has been done? Some work has been done, okay? If some work has been done, can I say that work is also energy? Okay, work is also energy. Now let me tell you what it is. So for example, surface tension is given by force per unit length. Force per unit length. Let me do one thing. Let me multiply it with delta L and divide it with the delta L. Delta L is the change, this change. Delta L. Let me multiply it with delta L and let me divide it with delta L. So what is this force into distance? So force into distance is the work done. Go to your elementary classes, class 11th, class 12th. What is work done? Force into the distance traveled. That is the work done. And what is work? Work is energy. So this term force into distance, this is known as the surface energy. That is the energy required or the work done for this shape this displacement, that is delta L. That is the surface energy. Okay. So this surface energy, so I will say that surface tension is equals to, this is surface energy divided by L into delta L, and the unit of L into delta L is actually meter square or mm square or whatever. So I will say that surface tension is equals to surface energy per unit area. Simple. Surface energy per unit area. Surface tension is equals to surface energy per unit area, or surface energy is also classified as surface tension multiplied by the area is known as the surface tension, surface energy. Clear? So that is surface energy. Now let me again explain you what is surface energy. For example, you have a bubble. You must have seen that if you go to some mela in a village or some, you can say, a fair. So you must be seeing that there are the street vendors. They have some small device. If you put it in the soap solution, if you just blow it, you will have bubbles. Have you seen that? Okay, bubbles are coming. Okay, so how much energy or how much work has been done to form that bubble? It can also be termed as a surface energy. Because earlier there was no surface, if you dip it, there is no bubble, but if you blow it, there is some bubble coming out. So on the the surface of the bubble, there is some surface tension. Okay, so how much diameter of the bubble you have formed, this bubble also has some surface tension, so you can get the surface energy. So how much work have you done to blow a bubble? That is also surface energy. Simple. Clear? So question. Can a liquid be wetting for non-surface and non-wetting for some other surface? Yes, a liquid can be a wetting for a particular surface and can be non-wetting for another surface. It can be possible depending on the type of surface. And depending on the adhesion, depending on the force of adhesion, it can be. Clear? So that is surface energy. So when we will be solving numericals, so I will also be solving some numericals on surface energy. So that is what surface energy is. Okay. So these were all the properties of a fluid. Starting from the mass density, then going to the weight density, specific weight, then we had the specific volume. Okay, specific volume, we have the surface tension. In the surface tension we studied about the wetting and non-wetting liquids. Okay, now the next thing is that we have to study something about the surface tension also. Okay, so now let me rub this, and now let us study the cases of this surface tension. So what are the various cases in surface tension? Various cases in surface tension. Okay, so now some cases in surface tension. Some cases in surface tension. Some cases in surface tension. Clear? Now, first of all, let us understand about a water droplet. A water droplet. Water droplet. Clear? First of all, let us understand about a water droplet. Clear? Now, let us say that you have a water droplet like this. You have some water droplet. Okay? If obviously there is some pressure inside the water droplet, I am taking an individual droplet just to see how much should be the surface tension, how much should be the pressure. If the inside pressure is very high, what will happen? This water droplet will burst. Clear? If the inside pressure is very high, what will happen? This water droplet will burst. If the inside pressure is very small, what will happen? The size of the droplet will decrease. Why? Because some surface tension is also acting. Along the surface. There is some surface tension acting along the surface. Clear? Some surface tension is actually acting along the surface. Now what can I do is that, so if I break this water droplet into two parts to analyze what can happen, if I break it into two parts, so it will be happening like this. So this is one droplet, half droplet here, okay, and half droplet here, and half droplet here. So pressure is also acting. So the pressure is also acting, which is trying to burst this water droplet. Some pressure is acting from inside, which is trying to burst this water droplet. And there is some surface tension also on the surface. Clear? There is some surface tension also on the surface. Now what will happen is that, for the equilibrium condition, let us consider surface tension to be equal to sigma Newton per meter or kilonewton per meter, whatever you want. Sigma. Now this sigma is acting on the surface, so that is actually equal to sigma into pi into d. For the equilibrium case, when it is just about to burst, so that should be equal to P, the pressure acting, multiplied by pi by 4 into d square. If this pressure is very high, it will burst. If this pressure is very low, sigma is very high, its surface area will decrease. For the equilibrium case, it is neither bursting nor decreasing the surface area. What we do is that, let us take the equilibrium case. So what will happen is that, so this pi get cancelled out, dd get cancelled out. So P will be equal to 4 times of sigma divided by d for a droplet, water droplet. So pressure should be equal to 4 times of sigma divided by d for a water droplet. Okay, so let me see some questions. So what are the factors in which the surface tension depends? It depends upon temperature, a lot of factors. Don't worry, we'll be coming to that also. Don't worry. It depends upon the temperature, viscosity and other factors also. It depends. Sir, why is the surface tension calculated on length and not on the area? Okay, so who is this? Aditya. So Aditya, actually surface tension is a surface property. If you are considering the whole area, then surface energy comes into picture. If you are considering the whole area, then surface energy comes into picture. So the definition of surface tension is the force force per unit length of the, you can say what are the peripheries. If the whole of the area is taken into consideration, then we have the concept of surface energy, not surface tension. So surface tension has been, you can say, has come into picture just to make you understand how much of the force is acting per unit length. But if you are considering area also, then surface energy will come into picture. Okay, so for a water droplet, so P is equals to 4 sigma by D. If P becomes greater than 4 sigma by D, it will burst. The water droplet will burst. Okay, so for the equilibrium condition, the pressure inside a water droplet should be equal to 4 times of sigma by D for equilibrium conditions. And questions have been asked from this formula also. Questions have been asked in GATE examination. Clear? Now let us consider a soap bubble, or just a bubble, or a soap bubble. Soap bubble. Okay, now what will happen to a bubble? Okay, so a bubble has air inside it and air outside it also. But if the air inside is very high, what will happen? The bubble will burst. Okay, and that bursting has been counteracted by the surface tension. That bursting, so that it does not burst. So what is the counteracting force? That is the surface tension. Surface tension is trying that it should not burst, and the internal pressure, if it is very high, it will burst. Clear? So now let us discuss about the surface bubble. So this is a surface bubble. Here also we have air, and outside also we have air. We have some pressure P inside, some pressure P outside. Some pressure is there. Okay, what is the difference in pressure? The difference in pressure is P inside minus P outside. P inside minus P outside is the difference in pressure. Delta P or P, whatever you want to call it. That is the difference in pressure. Now, if this pressure is very high, it will burst. Clear? Now, for the equilibrium condition, and what is the resisting force? That is the surface tension is the resisting force. The surface tension is the resisting force which will not try it to burst. Clear? Now, let me take again one section like this. The same analysis, okay, but here in case of a bubble, so let us say this is a bubble. My diagram is not very good, but still this is a bubble. But a bubble will have two surfaces. Because if you see a bubble, so inside also it is air, outside also air. So there will be a very small thickness of the bubble also. So that is the small thickness of bubble like this. Small thickness of bubble. So pressure is acting. Inside pressure is acting. It is trying to burst this bubble. And surface tension is acting. Surface tension is acting on the surface, which is trying to stabilize this bubble. And the internal pressure is trying to burst this bubble. Clear? Again doing the same thing for the bubble also. Let me change the marker. For the bubble also. So now, but in case of bubble, the sigma is acting on two surfaces. So one surface is this and another surface is this. We have two surfaces. So on two surfaces the sigma is acting. And the thickness is very small, so I will neglect the thickness. But it is very small. Clear? Sigma into pi into d, but we have two surfaces multiplied by 2. It will be equal to same p into pi by 4 into d square. P into pi by 4 into d square. Clear? So pi will get cancelled out, d get cancelled out. Okay, so it will be equal to, p will be equal to 8 times of sigma divided by d. 8 times of sigma divided by d. P will be equal to 8 times of sigma divided by d for a soap bubble. So it means that, what does it mean? It means that if the pressure is greater than 8 times of sigma by d, the bubble will burst. So for the equilibrium condition, so that it should not burst, there should be the pressure. There should be the maximum pressure. Questions have been asked like this. The maximum pressure in a soap bubble required so that it does not burst or it is about to burst. and sigma will be given to you, diameter of the bubble will be given to you. So simply P is equals to 8 sigma by D, you will get the answer. You will get the answer. Clear? So we will proceed also, don't worry, we have jet also after this. So till now, let me put the mark. Till now, if you have any doubt, till now, because there are some doubts which I will be clearing when I will be talking about the Reynolds experiment regarding, for example, there was some characteristic strength doubt, characteristic length was there, a doubt was regarding characteristic length was there. Okay, there were some doubts regarding the type of liquids also that we will also be discussing, okay, that will also be discussing. Stronger, it increases the surface tension, because it increases the surface forces, please repeat bubble, okay, don't worry, I will repeat, sir, please explain the equilibrium pressure condition again, okay, don't worry, let me again explain you, don't worry, okay, please explain once more, okay, let me again explain you, don't worry, sir, please explain this pressure inside a water droplet, okay, so let me again repeat this, now let me again repeat this. Clear? So now, first of all, let us understand the surface tension is a surface force. It is acting on surface. It is trying to stabilize a body. For example, if you have water droplet, obviously this water droplet has some pressure inside it, it has some pressure outside it. If the inside pressure is very high, if the inside pressure inside the bubble is very high, what will happen? So for example, I have a globe here. Because I always keep on looking for some examples. Let us say that if it does not break, okay, let us say that this is a soap bubble. Okay. Now it has some pressure inside and it has some pressure on the surface also. So the surface pressure is trying to make it a spherical thing. It is trying to stabilize it. But if the inside pressure is very high, what will happen? It will burst. Okay. Similarly for bubble also, similarly for droplet also. Okay. Now let me explain you here. Now for example, this is a water droplet. This water droplet is filled with water. Water is everywhere inside it. In this spherical, water is everywhere. So internally also it has some pressure, outside also it has some pressure. But if the internal pressure is very high, what will happen? It will burst. So what is the destabilizing force? The internal pressure is the destabilizing force. What is the stabilizing force? The surface tension is the stabilizing force. The surface tension wants that it should not burst. So what is the equilibrium criteria? At what pressure, maximum pressure it will burst? When this inside force will become equal to the outside force. We know that surface tension is measured per unit length. So what I do is that sigma, and it is acting per unit length. It is acting on a circumference. Sigma into pi into d. It acting on length multiplied by pressure is acting on the whole area. Whole area of this bubble will be equal to P into pi by 4 into d square. Even if you have don't understood this, just compare the units, you will get the answer. So unit of surface tension is Newton per meter. I have to multiply it with meter to get Newton. The unit of pressure is Newton per meter square. I have to multiply it with meter square to get Newton. So Newton will be balanced. Clear? So sigma into pi into d, it will be equal to P into pi by 4 into d square, and the maximum pressure inside a water bubble is 4 sigma by d. But as far as a bubble is concerned, a bubble has two surfaces. Obviously, if you see that inside bubble also we have air, outside also bubble we have air. But air, the bubble is made up of some water. Obviously, that water will have some very small thickness, where it will be very thin. Okay, it means that we have two surfaces. This is the outer surface and this is the inner surface. Let me take a marker. So this is the outer surface and this is the inner surface. And surface tension is acting on the surface. If it has two surface tension will be acting twice. So it will be one on the outer surface and one on the inner surface. Clear? So sigma into 2 times of pi into d. It will be equal to P into pi by 4 into d square. So P will be equal to 8 sigma by d. 8 sigma by d. Clear? Now let us come to a water jet. Now let us come to a water jet. Sir, what if the thickness is large t? If the thickness is very large, very large, then you have to measure it sigma into pi into d1 plus sigma into pi into d2. If the sigma is constant. If sigma is constant. Okay. Now third case is we have a water jet. The third case is a water jet. A water jet. Now for example, we have a nozzle. Let us say this is a nozzle. Okay. This nozzle has some surface area. Okay. Some water is coming from pressure. Okay. It is going from the nozzle. Okay. I am taking this section. Let us say this length is L. I am taking this section L. Now if I analyze it, this length is L. If I analyze it, if I cut it into two parts, so the below portion will be like this. So diagram should be, because I am very poor in diagrams, okay, so still it will be like this. Okay, if I cut it in two parts, you can see that if I cut it into two parts, it will be like this. Okay, so here we have some surface tension will be acting on the surface, and inside we have some pressure. Some surface tension is acting like this. Let the diameter of this bubble is small d, and this length is L. And the diameter is, let us say, small d. This diameter is small d. Clear? So now the inside pressure, if the inside pressure is very high, what will happen? It will go like this. If the inside pressure is very high, it will go like this. But if the inside pressure as well as the outside surface tension, they are in equilibrium, or the surface tension is very high, it will go like this. Otherwise, what will happen? The water will come out of the nozzle and it will go like this. It will scatter. It will scatter. If the internal pressure is very high. Now, to balance it, again doing the equilibrium condition, so pressure is acting on this surface area. This is a surface area on which the pressure is acting, because it is continuing. I am just taking a section, it is continued. It is continued here and here also. Right? So pressure is acting on this surface area. This is L into D, a rectangle, L into D is equals to, and the surface tension is acting on this surface and on this surface. So sigma into 2 times of L. So sigma, so LL get cancelled out. So P will be equal to 2 sigma by D. Now let us compare the three. So let me write it here. So for water droplet, the maximum pressure was 4 sigma by D. For bubble, the maximum pressure was 8 sigma by d. Clear? And for jet, okay, for jet, the P was 2 sigma by d. 2 sigma by d. Okay, so that is how we can compare this. That is how we can compare the three cases. Okay. Clear? That is how we can compare this. Okay, so let's proceed. Now questions have been asked from the water droplet, questions have been asked from the bubble also, but questions have not been asked from the jet. From jet questions have not been asked, but they might be asked in examination, that the pressure required for the stability of a jet. So sigma will be given to you, T will be given to you, everything will be given, so you have to determine it. Okay. Note it down, then we will proceed. Okay, getting it?
Yes, sir.
Okay. Are you also making notes?
Yes.
Okay, so now let us go to the concept of adhesion and cohesion again, because that will be used in capillary action, because now slowly we are moving to the capillary action. Okay, so now let us go to the concept of adhesion and cohesion again. Shall I rub this? Adhesion and cohesion. Clear? Now what is adhesion? Adhesion, the forces between different media or different particles is called as adhesion. As far as the cohesion is concerned, just go to the word co. Co means of the same nature, right? So force between same media or particle. Clear? Now we have understood what is adhesion and what is cohesion. We have also discussed that, for example, if adhesion is greater than cohesion, then that type of fluid is known as a wetting fluid, because it tries to cover the maximum area, and it tries to wet the surface. Right? So wetting fluid. Right? And if cohesion is greater than adhesion, that are known as the non-wetting fluids. wetting fluids, non-wetting fluids that are known as the non-wetting fluids. Now, if I consider this wetting fluid, for example, water, because we will be basically dealing with water. So, if I consider this water, if it is a wetting fluid, it will try to cover maximum area. So, the shape will be like this. The shape will be like this. Now, let us understand the contact angle. Always remember that the contact angle, just go to the word contact angle. So how much angle is there between the contact? Contact with what? Contact with the surface, right? So for example, if you draw a tangent like this, so this is the contact angle theta. And you can see that theta is less than 90 degree for wetting fluids. Clear? Because I have seen that a lot of students making mistakes in calculating the value of theta. Sometimes in question, just to confuse you, this angle is also given. Sometimes just to confuse you, this angle is also given. And I have seen that while determining the capillary rise or fall, students are using this angle. No, this is the angle, this angle. So draw a tangent and the angle between the surface and this. Similarly, if the cohesive forces are greater than adhesive forces, it is a non-wetting fluid. And in non-wetting fluid, it tries to have the minimum area of contact with the neighboring friends, but tries to have the maximum exposure with the surrounding friends. Example I gave you, right? So how will the profile would be like somewhat like this. Again, what you do? You draw a tangent to the surface. So draw a tangent like this, and the angle between this surface and this tangent, this angle is theta. So here also this. So this angle is theta. Clear? So that is the angle of contact. So you can see that the theta is greater than 90 degree. So I can say that here the theta is greater than 90 degree, and here for wetting fluid theta is less than 90 degree. For wetting fluids and for non-wetting fluids. So almost the time is, what is the time now? 3:30. Okay. So let me do one thing. Let's call it a day. Okay, because we have studied a lot of concepts. Okay. So tomorrow in the next class, the first thing which we will be doing is that whatever we have studied till now, we will be solving numericals. Previous year gate numericals as well as some other numericals which I think that okay, these numericals are some important numericals. So we will be solving all the different type of numericals. So we will start with numericals, and then we will be tomorrow we will be discussing about the capillary rise and capillary fall and why does it actually happen. The capillary rise and capillary fall, we will be discussing that. Okay. So let's call it a day and let's meet tomorrow. Let me see some questions. So done. Okay. Is there any liquid with theta is equals to 90? I have to see. There is a liquid in which theta is also 90 degree. I forgetting its name. It's vinyl something. Tomorrow I will come with the name also. Okay. Theta also 90 degree. Okay. So sir, draw the contact angle in conical vessel. Okay. Let me draw it. Okay. Okay, sir. Okay. Okay. Specific gravity y, then y density calculated for change temperature. Okay. Don't worry. I have noted all your questions. Don't worry. So tomorrow we will do one thing. So tomorrow whatever the questions you have, tomorrow first of all I will solve all your questions. I will be taking a screenshot of whatever the questions you have. So tomorrow first of all we will be solving your questions, then we will be solving the numericals, and then we will going to the next theoretical portion. Okay. So don't worry. Even if you have a single bit of doubt, don't worry. I have taken all your questions. Tomorrow, first of all, I will be solving your doubts, whatever doubts you have. Conical angle, how is the angle? Don't worry about everything, right? So I will be solving all your doubts, and after that we will be solving numericals, and after that we will be coming to again the capillary rise and capillary fall. Don't worry, everything will be solved. Okay, so let's call it a day because it's almost time. Okay, let's call it a day because some other faculty will be coming to teach you. Okay, so let's call it a day. Okay, thank you everyone, thank you. Okay, so thank you.